Here we're going to look at qubit ordering in the IBM quantum experience. We're going to dive into some details using Qiskit. In class, we've learned that when we look at quantum state in ket and vector notation, we use the convention where we go top down to specify the qubits in the quantum circuit and left to right when we express those qubits in the quantum circuit as a ket. So that reflects the following in vector notation, giving us the final vector that we use to represent the quantum state as a whole. So our top qubit is to the left in the ket, and our bottom qubit is to the right of the ket. Qubit order influences ket, which in turn influences the quantum state vector. When working with Qiskit circuits, you might have noticed something a little different with respect to qubit ordering. We have our typical convention, and then in Qiskit, we have this flipped convention where we actually go from bottom up, representing the elements within the ket. We have a different vector notation associated with the state. So we have the same state, but the elements within the vector are reconfigured. So here we can see that the middle two elements are swapped within the vector. Let's analyze the quantum state within Qiskit. So here we have our circuit for the C0 gate, and we have two qubits interacting within the C0 gate. Since our control is 1 and our target is 0, we're going to have an output of ket 1, 1. And we can see the state vector for the input state and the output state using our typical textbook convention of top down, left, right when filling out those kets. If we're to express this state using the state vector simulator within Qiskit, we can see that the output state has those middle elements switched. This is because our qubit ordering is in reverse. If we're to look at the output state using the state vector simulator as well, even though our state has our qubits flipped, the ordering difference doesn't change our state since we have a 1 and a 1 present in the ket, resulting in the same vector. So we can see that it's very important to pay attention to qubit ordering within your circuit because that can influence what your final state representation is in vector notation. Let's look at some quantum circuit matrices. Here we have a circuit that would look like the following in the textbook convention. In Qiskit, since we have a different order for our qubits, we have a different resulting matrix. We can use the unitary simulator to find out what the matrix is for a circuit within Qiskit. Because we have the flip in our qubit ordering, we have a different matrix that represents the operation, even though the operation is the same. If we want to reverse the order of our qubits within our Qiskit circuits, we can do so with reverse bits. So here we have our two circuits that we built earlier, and when we reverse our bits, our new outcome is as we expect. So it matches the conventional ordering that we would find in most quantum textbooks.